Our next guest is Andrew Goldberg. He's a principal researcher at Microsoft Research Silicon Valley, and his work focuses on creating algorithms for real-world problems. One of the interesting problems he studied is how to find the shortest path in really, really large networks in microseconds. So he's going to tell us a little bit about algorithms for doing that.
And recently I've been working a lot on shortest path algorithms, especially motivated by GPS navigation applications. So basically, how do I get from A to B?
That's great. So now how does, when you analyze this problem, that problem itself is fairly classically studied. What are the new wrinkles in it that come up, and why do they come up?
So the new wrinkles came up when GPS navigation became very, very widely used, and also GPS maps became continent-sized and detailed, digital maps. And then you really wanted to solve the problem much faster than in linear time. Basically, when Bing Maps or Google Maps gets a request, it doesn't have the time to look at the whole map. So linear time algorithms like your classical Dijkstra's algorithm are not good enough. And the new wrinkle was preprocessing. So you want to preprocess your graph to be able to answer queries very, very quickly, sort of in polylogarithmic time if you want to put your theory hat on. During last 15 years or so, there was a lot of research both at our group and also in many other places. And there have been very nice algorithms developed, which 10 years ago I wouldn't have believed that it's possible. But basically, these algorithms can answer queries in microseconds on continental-sized networks.
Wow. And it doesn't pre-store all possible pairwise
no,
shortest paths.
Just to give you an idea of a scale, a continent-sized network has tens of millions of nodes.
Wow.
So 10 million squared is too big even for today's huge disks.
Are there any relationships between the kinds of graphs that you get in highways and the kinds of graphs that would come out of a social network?
We did a very, very recent study. It's under submission now. And we studied some of the publicly available networks, and this hub labeling algorithm I want to talk about next actually works fairly well for this kind of networks like coordinate networks and so on. But for example, it doesn't work so well for small world kind of networks.
Okay, interesting. All right, good. So if you wouldn't mind telling me a little bit about the algorithm, I think that would be really interesting.
So let's talk about implementing just a distance oracle. So basically, given 2 points, you want to tell the distance between these 2 points.
Okay.
So the algorithm first preprocesses the graph, and for each vertex it computes labels. And let's say, for simplicity, the graph is undirected.
Okay.
Then a label of a vertex is a set of vertices, which we call hubs, and distances to these hubs from the vertex. So each vertex has a label. Okay, and these labels must have the following property. If you take any 2 vertices, their set of hubs has to intersect, and the intersection must contain a vertex on the shortest path between them.
Okay,
and why it's important is that for this vertex, if you sum up the distances to the 2 hubs, which you have, you will get the shortest path distance.
Somewhere there's also all hubs shortest path distances stored?
No, for each vertex, you have a set of hubs.
Right.
From this vertex to its hub.
Oh, I see. Oh, and they have to share a hub
on the shortest path.
that is also on the shortest path. I see.
Right. So this is a fairly strong property. So the easy way to do it is you say, okay, for each vertex, all other vertices are its hubs.
Then you're guaranteed.
Then property holds.
Yes.
But then your query time is order of n.
Right.
And what you really want is small labels.
Right.
And it turns out that some graphs have small labels, and the reason why this works well on road networks is that we can compute labels for, say, the graph of Western Europe with about 18 million vertices. We can compute labels of size about 70.
70, 70.
Yes,
Out of
Yes.
how many million did you say? 16 million?
18.
18 million. But
And
you only
this
need
makes it
70.
Very, very fast. So if you think about it, if you sort this hub by node ID, you have two arrays, and you just need to intersect these two arrays of size 70, which you can do like a merge sort with very good locality.
Yes.
So the time becomes below a microsecond.
Wow.
It's really very, very fast.
But this is not a very intuitive concept to me. So what are these 70 for a given? So now we're talking about like individual intersections in Europe, right? This is like Piccadilly Square or something like that, or the northeast corner of Piccadilly Square. And there's 7. You only need to know from there the distance to 70 other places in Europe.
This is the amazing thing, and that's why people thought that this wouldn't be practical, because if you think about it, we'll probably need thousands.
Right.
But the surprising thing was that you only need a much smaller number. So if you think about it, long range, it's basically intersections of major highways.
Okay.
And there are not that many of those.
Right.
And sort of locally, it's intersection of state highways, and more locally, it's intersection of major streets. The bad graphs for this kind of algorithms are grids. But fortunately, there are no big grids in the maps, and even there are grids, like in Manhattan, it's only 10 avenues wide, so it's not very big. And there's Broadway, which breaks the symmetry. So things are not as bad as one might think.
That's fascinating. So of the 70 places, I could imagine that some fraction of them are for real long distance travel, like between countries, and
Right.
some other fraction of them are for more within the country but far distance, and then another fraction of them are for within the region of the country. And about how is it sort of equal buckets for each, or for really far distance you only need a small number, but for local you need more? Like what's the distribution like?
So it's roughly uniform as you increase the scale exponentially.
Wow. Wow.
That really depends on where in the country you are.
Okay.
Because in that densely populated area, you need more local things. If you are in the middle of nowhere,
There's only one way out.